Okay, hello. Today we are getting back into probability distributions. And before we start applying the new concepts that we're learning in this unit of combinatorics, I want you to just kind of get your brains into that setup again. So I want you to determine and interpret the expected value for this non-uniform probability distribution of lottery prizes. So before I ask you to pause and do that, I want to just talk about what this means by non-uniform probability distributions. So a uniform probability distribution, all of the probabilities would be the exact same. Non-uniform means they're not the exact same. Now today and a little bit later on this unit, we're going to look at two very specific non-uniform probability distributions. And so if I gave you a distribution and I asked you to name it, I'd want you to use these more specific names. But a lot of the times they don't fall into one of these categories. And so we just say non-uniform. We can't specify it any bit more. We will talk more about that when we're comparing the types of distributions in a later lesson. Okay, so don't focus too much on that just yet. All right, so pause this video right now, and then I want you to go through and remind yourself, how do you calculate expected value? If you need to look back at your notes, look at your formula sheet, go through and calculate the expected value, and then unpause when you have that done. Okay, so hopefully you have unpaused and you tried that on your own already. And in order to calculate the expected value, we need to find the sum of all of our x's times those individual probabilities. So the easiest way to do that is to organize it right on your chart. So that's why I gave a third row here. So you'd go through and you'd make a third row of x times probability of x, and then you would add that all up. And we can see that work here. So again, this formula right there is on your formula sheet, so you can use your formula sheet to do that. This label comes from here, right? Anytime you see a summation, you think make a row or a column, depending on how you have your stuff organized. And then you're going to do that particular piece. So the label is the same as this. Sometimes people are labeling this as E of x, and it's not E of x. E of x, the expected value of x, isn't till you take the sum. So it's not till you get to this section right here that it's E of x. Okay? To remind ourselves how we got all of these numbers, so this column, for example, to get this $2.50, I multiplied $25 times 0.1, and that gave me $2.50. Note that it's still in dollars, because it's dollars times just a decimal still gives me dollars. And when I add that up, I get $6.25. So again, that one is dollars, missing my dollar sign. What does that mean? It asks me to interpret in the question. So the meaning of that expected value, again, is not what I expect to get. If I buy a single lottery ticket, these are the only possible values I could get, right? And most of the time, 50% of the time, I'm actually going to get 0. So that's kind of what my brain would expect to get if I bought a single ticket, right? What this $60.50 means, if I bought many, many tickets, like really, if you bought all the tickets that were available, on average, you would win $6.50 per ticket. Okay, so the key words when you're explaining your expected value is it's an average amount of whatever you're measuring per item if you did many trials. So in this case, buying many tickets, you could say infinite trials, infinite tickets, something along those lines. All right, so today we are learning a specific kind of non-uniform distribution called hypergeometric probability distributions. These types of problems all use combinatorics in order to calculate the different probabilities. So again, we have all the skills to do the calculation for the probabilities. That's all dependent on yesterday's lesson and the day before. Today we're looking at just how can we make that into a probability, and then how can I make a probability distribution based on that. So we're going to dive right into an example, and then based on that example of just calculating one probability, we're going to generalize it to how do we calculate the probabilities for any value of a random variable, and that will give us our probability distribution table. All right, so our example is our bag contains 8 green marbles, 3 white marbles, 5 red marbles. You reach in and you are pulling out 5 marbles. Okay, and let's say for the sake of this question, we are going to grab those 5 marbles just at once in our hands, like just we're grabbing a handful of marbles, okay? And the question asks, what's the probability that you select exactly 3 green marbles? So we're putting our hand in, we're grabbing 5 marbles total. What's the probability that exactly 3 of those are green? All right, so the big idea behind probability again is number of ways of getting what I want, number of ways of getting the criteria, in this case 3 green marbles, over top of what's just the number of ways that I can pull out any 5 marbles, ignoring color. Okay, so I start by just saying what's the probability of getting exactly 3 green. Oh, actually I have this all done already in behind. Sorry. So I say, what's the probability of getting exactly 3 green? So that's going to be the number of ways for me to select 3 green. And though, no, I still have to pull out 5 marbles. So I'm selecting 3 green. I have to select 2 that are not green. I don't care if it's white or red. It just can't be green. So I'm going to select 3 green and 2 not green. That's the number of ways of getting what I want. Number of ways of getting what I don't want is on the bottom, or sorry. Number of ways of getting total, just any 5 marbles, ignoring the color, is on the bottom. Okay, so now we break this down. How many ways can I select any 3 green marbles? Well, there are 8 green marbles to start from, and I want to select 3. What option or what mechanic do we use to do a number of selections? That's a choose statement, right? So I'm going to do 8, choose 3. Then I'm going to do my number of selections of not green. How many not green? There are 3 and 5. So again, that totals to 8. So I'm going to do 8, choose 2 in this case. Over top of total number of marbles, 8, 11, 16, 16, choose 5. And here are those values coming up. There we go. So again, 8, choose 3, number of selections of 3 green. 8, choose 2, number of selections of 2 of the not green, over top of 15, choose 5. Then I just plug that in my calculator. You can work out the top and work out the bottom, and then use your fraction button to reduce that fraction, or you can actually just do it all at once in your calculator, pressing the fraction button instead of the division button. So just kind of keep that in mind that your calculator can do these reductions for you, but we want to keep our answers as reduced fractions in our math paragraph. So we get 14 over 39 as a probability of selecting 3 green marbles, exactly 3 green marbles. All right, now, before we move on to convert this to a probability distribution, I want to talk a little bit about what makes this special type of non-uniform distribution called a hypergeometric distribution. So in a hypergeometric distribution, oftentimes we are reaching in and we are pulling out a bunch of things at once, okay? Or I could reach in and pick one, don't put it back. Reach in and pick a second one, don't put it back. Reach in and pick a third one, don't put it back, okay? And then we would have dependent trials because probability would change as I moved on. The mathematics, whether you do it using dependent probability or whether you do it using chooses, will give you the same answer. So I tend to always do the choose method when I'm doing a hypergeometric distribution. It makes it a little bit faster. Okay. The other thing that we think about in this case is we have one type of outcome, in this case green marbles, that we would consider a success. That's just the number of things that we're actually caring about. And we have a second type of outcome, which we often consider a failure. And that just means those are the things that we're not really specifically caring about. That's all. Okay. And then we're always given number of all these different things in our question. So we always have that piece of information. Okay, so that kind of goes along with what is on this slide. So again, the properties of hypergeometric. It's a series of non-identical dependent trials, meaning if you are selecting one thing at a time, you are not putting it back. Or it's just one trial and you select a whole bunch of stuff at once. I would say more often than not, it's that one trial and you're doing multiple selections at the same time. You have a known number of trials, which could also be the number of things you're picking, okay? You have a known number of total objects. So in that last case, we knew how many total marbles there were in the bag. And again, for this total number of trials, we knew we were picking 5 marbles. There are 2 outcomes for each one, often labeled as success and failure, okay? Success is what you are counting. So we were counting green marbles. Failure is what you are not really caring about. It's not being specific. It's just the leftover pieces. So that was the not green. Each of those have a known number. So the total number of successes is known. We knew the total number of green marbles. And we knew the total number of not green marbles as well. So all of that was given in the question. And our random variable is the number of outcomes of one specific type. Generally the number of outcomes of this success. So we were looking at the number of green marbles. We specifically looked at the case for 3 green marbles. So this formula right here is how I always calculate a hypergeometric probability distribution. I'm just looking at how many ways can I select my one type, how many ways can I select my successes, times, because it's an and, how many ways can I select whatever else I have to select, whatever is like left to fill up my handful, divided by the number of selections total, ignoring the type. Okay, just like we did in the last example. The textbook and your formula sheet give you a formula sheet that looks like this. Just get this out of the way here. Okay. Note that it's got a whole bunch of different letters in there. Some people like to memorize what each one of those letters represents and use that formula. Some people like to just think about it in terms of the relationship of how many ways can you do things. It depends on which way your brain works. You can go either way. I find the people who use this top version have a better conceptual understanding of what's happening though. So just kind of keep that in mind. In here, that first A, choose X, that's the number of choosing your one type. So that's the number of ways to choose your successes. Okay, that would be the number of ways to choose your 3 green marbles. Number of selections of the other type is the number of ways to pick whatever else you need to pick. So the non-green marbles. The N choose R is the number of ways of picking anything. It's your sample space. It's your just total number of outcomes for picking any 5 marbles. Okay, so pause if you need a little bit more time to write that all down. Again, if you don't want to use that bottom version, you don't need to worry about what A and X and N and all of that stuff is. All right, so hopefully you paused, you wrote all of that stuff down. Let's go back to our example with the marbles. So this isn't a new example, that's the same stuff you have written down from before. So in this case, again, just to remind you, the green marbles are what would be considered as your success. White and red would be kind of considered your failure. Okay. And the random variable would be the number of green marbles. That's what we were counting. We wanted exactly 3 in that case, but this particular piece we would change for our probability distribution, which is what we're going to do next. All right, so this says create a probability distribution for this experiment where the random variable X is the number of green marbles selected. Okay, so we have to think, what are the possible different number of green marbles selected? Well, we know we can select 3 because that was what the original question asked for. Now it's not asking for that anymore. It's asking for a full probability distribution. So we have to think, well, can I select less than that? Yeah, I can actually select 0 green marbles. Or I could select 1 green marble, or 2 green marble, or 3 green marble, or 4 green marble, or 5. I can't select any more than 5 because I'm only pulling out 5 marbles, right? And I can select no green because there are enough the other kind to select all 5 of the other kind. And we already calculated that first one was 14 over 39, if I remember correctly, when x equals 3. So to calculate the other ones, I could go through and I could say, all right, what's the probability when x equals 0? Well, that'd be the number of ways to select 0 green marbles. So without writing my end statement, just skipping a little bit of work to fill in the probability distribution, I have 8 green marbles and I'm selecting none of them. That means I have to select 5 of the other kind of marble, the not green, and there are 8 total of those. Over top of selecting 5 marbles from any of the marbles. So 16, choose 5. When you work that out, you end up getting 1 over 75. So what I'd like you to do right now is I'd like you to pause, and I want you to calculate what's the probability when x equals 1, what's the probability when x equals 2, what's the probability when x equals 4, and what's the probability when x equals 5. Okay, go through and figure out what all of those probabilities are and then unpause to see the answers. All right, so probability when x equals 1, again, we're not showing full communication here, just writing it down so you can see how I did it. This would be 8 green marbles, and I want to pick 1 of them. And then I need to pick 4 other marbles from the 8 white and red marbles. Over top of, this is always going to be 16, choose 5. Punching that in the calculator, you should have ended up getting 5 over 39. For 2, you have to change this number to a 2. So I'm going to end up with picking 2 green marbles, picking 3 from the 8 other colors. Again, still over top of 16, choose 5. And we should have got 14 over 39. Or I could get 4 green marbles, 1 not green. So you should hopefully kind of recognize this as this is like the cases that we did before. This case, we have 4 green and 1 not green. But now we want it to be a probability, so we put it over top of our sample space, which is the total number of ways to do anything. And then this last one will be 1 over 78. Okay, so then it asked, we want to find the expected value. Actually, it didn't say to find the expected value in the question, but that's what I want us to do next. I want us to find the expected value. So, okay, we know that expected value, oops, let me go back. Can I go back? 1 second. Oh, I've lost all my values. That's okay. We can put those in really quickly and go back to calculating expected value. So remembering that expected value for any distribution, we can use this formula that's on the formula sheet. The sum of x times the probability of x. So that means I need to do x times p of x. Okay, so pause, go through and finish that off. Find x times p of x, and then sum it up, and then unpause when you're ready. All right, so if you've unpaused, hopefully you have these answers for your individual fractions. And then you went through and added all of those up. Just give me 1 second here. And you should have got 5 over 2 if you reduced. And this is, again, this is money, so I might as well just leave it as a decimal or convert it to a decimal. So that ends up being $2.50. All right, now let's think about what that means again. This means on average, oh, sorry, this isn't money. So that would be 2.5 green marbles, because this was about green marbles, not the lottery ticket. What does this represent? This represents that if I pulled 5 marbles out, many, many, many times. I kept resetting this experiment, and I did it over and over and over again, and I always picked 5 marbles. The average number of green marbles I would get is 2.5. Now, let's look back at our numbers again, right? We started, so in the bag, 8 out of the 16 marbles are green. What percent of the original bag of marbles were green then? That means 50% were green in the original bag. Okay? And when we're picking out 5, we noticed our expected value ended up being 2.5 green. What do you notice about 2.5 and 5? Well, again, that's 50% of 5. That's always going to work if we have a hypergeometric relationship. So there is a quicker way to find expected value when you have this type of relationship, a hypergeometric distribution. Again, most likely way we have a hypergeometric distribution is if we are pulling out a bunch of things at once. So you're grabbing a handful of items. But realize that it can also be you're selecting multiple items without replacement. So like cards would be another one. You pull one card, you don't put it back. You pull another card, you don't put it back. And you pick maybe 5 cards. And then we look at what's the expected value for number of clubs, for example. Okay? So, just to summarize again, most of this stuff on this page you've already written down. This is the new piece now. The expected value we can also do. You could still use the old way, but it will take a lot longer. If it's a hypergeometric, we can use probability of success on one trial times the number of trials. Probability of success on one trial for the last question was 50%. 50% of those marbles were green. So I would expect, if I were just picking one marble out, 50% of the time I would expect to get a green marble. Okay, but then I'm not picking one marble out, I'm picking 5 marbles, so the number of trials would have been 5. If you're obeying all the A and N and X variables, this second version of that formula would be that. The A over N is the number of successes out of the total number of elements. So that would have been 8 over 16. That's what gives us our 50% probability of success on one pull. R, number of trials or number of things you're pulling out of the bag. Okay, we'll do another one, a warm-up of these tomorrow as well in class. But for tonight, I want you to attempt the practice work that is listed on the unit outline.